Students, will continue with the revision that we had started. I think last class we were discussing the defects or imperfections in solids, right? So, which is nothing but deviation or irregularity in terms of arrangement of particles. So, we have two types of defects. One is called point defect, another one is line defect. In point defects, we have stoichiometric, impurity, non-stoichiometric. Again, there is further classification. So, I think we are finished with stoichiometric defects. It is vacancy, interstitial, Frankel and Schottky. Today, let us see the impurity defect. Okay. So, as the name suggests, this defect occurs due to an impurity ion creeping inside the crystal lattice. Okay. So this can be explained taking an example, the formation of NaC. Suppose if I have a regular NaCl structure or crystal, what will be how will be the ions? It will be sodium followed by Cl minus, then again sodium, then Cl minus. So this goes on, right? Like this. Then I can write Cl minus sodium, Cl minus sodium, again sodium, Cl minus sodium. So it is a regular NaCl crystal. This would have been the structure. Now suppose when I am crystallizing NaCl from seawater, suppose strontium chloride creeps inside. A bit of strontium chloride comes inside this crystal. What will happen? Strontium ion, which is Sr2 plus, will occupy one of the sodium ion sites. So let us say this site. As it occupies this site, what about the neutrality of the structure or the crystal? Here you will see that number of plus charges will be more. So what it does, as it enters, it occupies one of the sites of sodium ion and leaves another side vacant. So the number of cationic vacancies produced will be equal to number of Sr2 plus ions. Understood? So now see, the charge becomes balanced. But when it leaves out one spot of sodium ion vacant, it leads to a defect, and that defect is called impurity defect. Now this is again a type of vacancy defect, isn't it? And this vacancy defect has occurred due to the strontium ion creeping inside and taking up one of the sites or sitting on one of the sites of sodium ion. Such a defect is called as an impurity defect. It is due to an impurity ion creeping inside the structure, and because of that, in order to always an inorganic compound has to maintain electrical neutrality. Okay. So one spot it occupies, another spot of sodium ion it will leave vacant. So this is your impurity defect. So far we have seen the stoichiometric defect and impurity defect. Now these two, are defects in which, even though particles will be missing, the stoichiometry of the structure is not, or the substance is not affected. So then we come to the third class. Then there we have non-stoichiometric. Okay. Now you can, if you see, you will see a number of inorganic compounds. They are there where the stoichiometry is not maintained. They are non-stoichiometric in nature, and this is due to the defects that are there in the crystals. Okay, so a large number of inorganic compounds are there which are formed due in non-stoichiometric ratios with respect to the elements that are there in that compound. Okay. So in this non-stoichiometric defects, we get two types. One is metal excess. Another one is metal deficit. And in this we get two types. Due to anionic vacancies. And the next one, due to excess of cations. Okay, so we'll see both non-stoichiometric defect, two classes. You have metal excess, metal deficit. In metal excess defect due to anionic vacancies, and metal excess defect due to excess of cations. The first one, now this can be explained using an example. Suppose if you take alkali halides like NaCl or KCl and expose them to vapor of sodium or sodium vapor. So by right now, so you have minus plus plus minus plus minus plus. Okay, so let us say it can be NaCl or KCl. Let us say it is NaCl. If it is exposed to vapor of sodium, then what happens? Let us say I will just draw the structure like this. So when it is exposed to sodium vapor, the sodium atoms will come and sit on the surface. Let us say this is a sodium atom that comes and sits on the surface of this crystal. So as this sodium atom sits, one of the Cl minus ions, okay, will leave its position. So let us say this Cl minus leaves this position and goes up. Okay, it comes here and then joins with that sodium to form NaCl. Okay. Now that is possible only if sodium gives an ion or gives an electron to form the sodium ion. Okay, so this now can combine with this to form NaCl. But the liberated electron comes inside and occupies the site that is left vacant by that Cl minus ion. Therefore, it is called as metal excess defect due to anionic vacancies, because that anion is creating the vacancy by going outside. Okay, and its place is taken by the electron that is liberated by the sodium ion or the positive atom that is there. Okay, so that comes in, occupies, and this, as soon as it comes, this electron is responsible for the color that is imparted. Therefore, this particular site is called far-bent center or far-bent center site. Some call it as far-bent center. So, it is nothing but the site that is vacated by Cl minus, occupied by the electron, and once this electron comes inside, it imparts color. Because of this presence of this electron here, it will impart color to the crystal. So you know, whenever NaCl you take and heat it, sodium ion always gives you golden yellow color. So when you heat also sodium chloride, you see that it gives you golden yellow color. So this is your metal excess defect due to anionic vacancies. Then we have one more, isn't it? Metal excess defect due to excess of cations. Okay, so from the name itself it is obvious here, cations will be more, or because of that, when they are more, they will come inside the crystal and occupy interstitial sites. Therefore, we will have a defect. Now this again is explained using the example of ZnO, zinc oxide, which is white in color. Okay, when you heat this, you will get zinc ions plus oxygen. So, suppose if it is like this, okay, now this is heated. That means, let us say, and this is going off in the form of gas. So this is living. So what will happen now? These are zinc ions. They come inside. Okay, they the interstitial sites. Therefore, they create this defect, and it is due to excess of cations which are there. They have crept inside the crystal lattice now and they are occupying interstitial sites. Therefore, it is called due to excess of cations. See, earlier if you think that you had Zn1O1. Now X number, let us say X number of zinc atoms are more. So the formula becomes Zn1 plus X O. Because of that, the excess positive ions will come inside, cations will come inside and form an interstitial defect. So this is, these two come under metal excess defect. Then the last one, metal deficit defect. Okay, so most of the compounds we also come across where we see that the proportion of the metal with respect to the other anion is not according to stoichiometric proportion. So one best example is, if you take FeO, okay, you will see that the amount of FeO is little bit less compared to O. So they are not in stoichiometric proportion. Here there is deficiency of this metal or the cation with respect to the anion. So it might be Fe 0.93 to 0.96 compared to O1. See? Is it? So the metal is in less quantity compared to the anion. So it leads to a defect and is called as metal deficit defect. Okay. So this is in brief the various types of points defects. Now we will go into properties of solids. In properties, the first thing or first property that you learn is the electrical property. Okay, so we have solids will show you some conductivity. There are almost 27 orders as far as the conductivity of solids is concerned. So you take any solid, it will show you some conductivity, and depending upon the conductivity range, solids can be classified into three types: conductors, insulators, and semiconductors. So what is the conductivity range of the conductors? It is around 10 raised to the power 4 to 10 raised to the power 7 per ohm per meter. This is the conductivity range of conductors. If it is insulators, it is 10 raised to the power minus 20 to 10 raised to the power minus 10 per ohm per meter. And insulators is around 10 raised to the power minus 6 to 10 raised to the power 4 per ohm. Okay, so depending upon their conductivity range, we can have three types of solids: conductors with this conductivity range, insulators with this conductivity range, and semiconductors or semiconductors with this conductivity range. Okay. Now coming to conductors. There are two types of conductors: metallic and electrolytic. Okay, so conductors are of two types: metallic and electrolytic. This is due to the flow of electrons. So metallic conduction is due to flow of electrons. This is due to the flow of ions. Okay. So, second, decreases with increase in temperature. Whereas increases with increase in temperature. Okay, so basic difference between them. Then you know, a metallic conductor can go on working, it doesn't have a shelf life. But you know, electrolytic conduction cannot go on and on. It is there till the ions are produced. Once the electrolyte stops undergoing ionization and producing the ions, it will stop. So we can say it has a shelf life. Okay. This doesn't have, this can go on and on because it's just flow of electrons. Okay. So, okay. Then there is one theory given to you that is called band theory, which tries to explain what actually happens in this conductors. Or why a solid will behave as a conductor, why it behaves as a semiconductor, why it behaves as a insulator. So, and that is band theory. Okay, so according to this theory, solids, especially metals, are very good conductors. They will conduct in solid state as well as in molten state. Okay. Now, the atomic orbitals, because again the electrical conduction in solids is due to the electrons. Okay, and it depends upon how many valence electrons are available per atom. Okay, more the number of electrons available, more will be the conductivity or the conductance. Okay. Therefore, what the theory says is, the atomic orbitals of metal atoms will combine and form molecular orbitals. And these molecular orbitals so formed are so close in energy so as to form a band. And if this band is partially filled, or if it overlaps with the next higher conduction band, okay, then under an electric field, the electron can move from one field to another field, and therefore it will show this conduction. So a conductor will have this type of structure. Either it will have this band which is partially filled, or this partially filled, if it is not partially filled, it will have another band which is of higher conduction band that is going to overlap. Okay, so that the electron can move from the lower band to the higher band. Okay. So now, if you want to show it graphically, see, I told you the atomic orbitals of these metal atoms will combine to form metallic orbitals, molecular orbitals, and they will be of, their energy levels will be almost the same, we can say, not same. So what will happen? They will come over one another, they will start overlapping, and therefore they will form a band. This band, if it is half filled, so if I draw, let us say this is the band of molecular orbitals formed by a combination of atomic orbitals. This band has to be partially filled. So this is your partially filled band. This is one scenario where now the electron has the space to move. Therefore, it will show you conduction. Okay. The second is let us say this band is fully filled. But it is overlapping with the next higher conduction band. So this is higher empty conduction band. So whether it has this or this, what will happen? Under the influence of electric field, the electron can move, and therefore it will show you that electrical conductors. Okay. This structure exists in all conductors. Okay. But if you take insulators, there is this band and there is the next higher conduction band. This is empty, no doubt. But the gap between these two bands is such that the electron cannot overcome this particular gap. So it is called forbidden zone. Therefore, conduction stops. So it behaves as an insulator. Then we have the third scenario where the semiconductor, what happens in a semiconductor? So in a semiconductor, there is this band, let us say, which is fully filled. And there is a next higher band. Okay, so what is the gap? The gap is very, very small between the two bands. Therefore, the electron can jump over and continue its journey in this band. So it will show you some conductance. So this will happen inside a semiconductor. Understood? So this is a bit of a graphical explanation given using the band theory, which tries to tell you why a solid will behave as a conductor, why it behaves as a semiconductor, why it behaves as a insulator. Okay, so this is the electrical property. Then the next part, let us take it in the next class.